So, usually when we pull out a map, there's this really ingrained expectation of, absolute cold objectivity.
Right, yeah, like, the map is just indifferent to whoever's looking at it.
Exactly. I mean, you look at a map of London or Tokyo, and streets are just where the streets are. The intersection of Fifth Avenue and 42nd Street doesn't, like, pack up and move just because you happen to be standing 3 blocks away.
Yeah, it exists in this totally absolute state. It's fixed.
Indifferent is really the perfect word for it. But what's crazy is the moment you step into the world of celestial navigation, that entire comforting idea of a fixed map just gets totally turned on its head.
Oh, absolutely. It forces you into this highly relative, entirely observer-centric
Like
reality.
it's a profound shift in how we're taught to think about geometry.
It really is.
Yeah.
So to wrap our heads around this today in our deep dive into the source material,
Hmm?
I want you to imagine something, like put yourself in the shoes of an early navigator.
Okay, setting the scene. I like it. Yeah, so you're standing on the deck of a ship. You are in the exact middle of the ocean. It's the dead of night. There is literally no land in sight for 1,000 miles in any direction.
And no glowing GPS screen to bail you out either.
Right, no landmarks, no electronics. You just look up, and above you is this dizzying, chaotic swirl of stars, just thousands of pinpricks of light.
Which is incredibly beautiful, but, if you don't know how to read them, it's just chaos.
Beautiful. Yeah, but terrifying if your life actually depends on knowing where you are. I
Yeah.
mean, the fundamental question here is, how do you bring order to that chaos?
How do you map it based entirely on where you are standing?
Exactly. Based entirely on the, 2 square feet of wooden deck you're standing on right now, because that's literally your only anchor in the entire universe at that moment.
And that right there is the core problem that navigators have wrestled with for centuries. And what's so fascinating about the materials we're looking at today, these lessons on daily motion and the horizontal system of coordinates, is how methodically they actually solve that problem.
Mhm. And what really struck me going through this isn't just that it's a bunch of abstract math. Like, by the end of this deep dive, you're going to understand how your specific physical location on Earth literally alters the geometry of the entire sky above you.
It's amazing. The sky just stops being this flat painting on a ceiling and becomes a full three-dimensional grid that you are the center of.
Right. And we're going to find the aha moments hidden inside all that math. Because once you see how the sky locks into your physical body, you are going to look at the night sky completely differently.
But to get to that point, the materials actually start by setting up a contrast between two completely different ways of mapping the heavens, like two totally distinct coordinate systems.
Yeah, the sources introduce the equinoctial system and the horizontal system. And I'll be honest, at first, having 2 different maps for the exact same sky just seemed completely redundant to me.
Well, yeah, it totally seems that way until you realize they serve entirely different but, codependent purposes.
Okay, let's start with the equinoctial system, though. Going through the breakdown, this one acts like that objective city map we were just talking about.
Right, it's fixed relative to the stars themselves.
Yeah, so the Earth could just vanish, and this map would still exist perfectly fine. And it uses these coordinates called declination and sidereal hour angle.
I know those terms sound super intimidating, but they're incredibly straightforward if you just think of them as the celestial versions of latitude and longitude.
Okay, let's break that down.
Yep.
So declination is like latitude.
Yeah,
Right?
exactly. Imagine taking the Earth's equator and just expanding it outward like a giant glowing ring until it hits the stars.
Okay, I can picture that.
That is the celestial equator. So declination is just a measure of how far north or south a star sits from that celestial equator line.
Gotcha.
So the star Sirius, for example, has a specific declination. It's always there, just like the Empire State Building is always at a specific latitude on Earth.
Okay, that makes sense. And the sidereal hour angle, that's the longitude part.
Essentially, yes. You know how on Earth we measure longitude starting from the prime meridian in Greenwich, England?
Right.
Well, in the sky, astronomers and navigators picked a specific fixed point. It's called the first point of Aries, and they measure the angular distance westward from there.
So with a declination and a sidereal hour angle, you basically have a permanent absolute address for every single star up there.
Precisely. It doesn't care if you're looking at it from a ship in the Pacific or like a desert in the Sahara. The address is the address.
The universal grid. Okay, but then we flip the page to the real star of the show today, which is the horizontal system. And this is where my brain had to do a bit of a backflip.
It's a big shift in perspective.
Yeah, because the coordinates here are called altitude and azimuth. And if the equinoctial system is the paper map of the city, the horizontal system is like putting on a virtual reality headset.
Oh, I love that analogy.
Mhm.
That captures the essence perfectly.
Right, because when you put on a VR headset, the computer placing you in the world makes you the absolute center of the universe.
Everything orbits your perspective.
Exactly. If you tilt your head back, the system redefines what up means based entirely on the angle of your neck. That's exactly what the horizontal system does. It describes the sky purely from your point of view.
And its reference plane isn't some absolute celestial equator out in space.
Mhm.
Its reference plane is your horizon, like literally the line where your sky meets your Earth.
So my immediate thought reading this was, why do I need the VR headset map if I already have the absolute perfect permanent map? Like, why bother?
Well, it comes down to the physical limitations of being a human being holding a tool. Think about what a navigator actually does out there.
Okay, they're standing on a pitching deck.
Right, and they hold up a physical instrument, a sextant.
Yeah, the brass thing with all the mirrors and little lenses.
Exactly. When you look through a sextant, you are measuring the angle between a celestial body, say a star or the sun, and the physical horizon you see stretching out in front of you.
Okay, I'm tracking.
You are measuring the body's altitude. The sextant has absolutely no idea where the celestial equator is. It can't see the sidereal hour angle. It only knows what your eye can see right now.
So you're basically capturing a piece of data from the VR headset view?
Exactly. You are taking a horizontal system measurement.
But I mean, knowing that a star is like 40 degrees above my horizon
Right.
doesn't actually tell me where I am in the world.
No, it doesn't.
Yeah.
And that is the crux of the whole celestial navigation process. To figure out your location on Earth, you have to compare what you actually see in your VR headset against what the absolute map says you should be seeing.
Let me see if I have this workflow right. So I'm on the deck. I take my sextant reading. Let's say I shoot a star, and its horizontal altitude is 45 degrees.
Right.
Then I go down into the cabin, turn on a little lamp, and I open up this thick, heavy book called the Nautical Almanac.
Ah, yes, the Navigator's Bible.
And I look up the exact time, and the almanac tells me exactly where that star is located on the absolute equinoctial map at that specific second.
And then the magic happens. Navigators call this process celestial sight reduction.
Sight reduction,
Yeah, you're mathematically reconciling the two maps. You take your personal relative observation, your horizon, and you force it to communicate with the universal absolute data.
But to make those two completely different maps talk to each other, you'd need, like, a translation guide. You have to meticulously define the architecture of the VR headset so the math actually works.
You do. You have to build the geometry completely from the ground up.
And building any structure starts with the ground floor. We need a
Mhm.
baseline. The sources actually spend an incredible amount of time detailing different types of horizons, which, honestly, I kind of scoffed at initially.
Oh, really?
Yeah, I thought, the horizon is just the horizon. It's the line out there where the water stops.
Oh, that's a very common assumption. But in celestial navigation, ambiguity is basically the enemy. Precision is quite literally the difference between finding an island and crashing your ship into a reef.
Fair point. Fair point. So the materials outline three distinct horizons we need to understand: the visible horizon, the sensible horizon, and the rational horizon.
Let's unpack the one we all know intuitively first, right? The visible horizon.
Yeah, the definition is pretty straightforward. It's the line where the sea and the sky appear to meet. It's what your physical eyeball sees when you look out over the ocean.
Right. But the text aggressively throws this out. It says, point blank, we can't use the visible horizon for the core math because it's affected by the observer's height of eye and atmospheric refraction.
Yeah, and the physical reasons for that are totally fascinating. Let's tackle the height of eye issue first.
Okay, let's do it.
So imagine you were standing barefoot on a flat, sandy beach, looking out at the ocean. Your visible horizon, the furthest point you can see before the curve of the Earth drops away, is maybe, 3 miles out?
Yeah, roughly 3 miles. So your line of sight hits the curve there.
Now imagine there's a massive skyscraper built right on that exact same beach. You take the elevator up to the 100th floor and look out the window.
Oh, your visible horizon is suddenly much, much further away, maybe 40 miles out.
Because I'm higher up, I can see further over the curve of the Earth.
But think about what that means geometrically. Your line of sight from the beach was relatively flat. Your line of sight from the skyscraper has to angle downward quite a bit to hit that new edge.
Right. The angle of the horizon has physically changed relative to me just because I went up an elevator.
Exactly. So if you're on a small sailboat, your visible horizon is at one angle. If you're on the bridge of a massive aircraft carrier, it's angled further down.
And that's a localized variable that ruins any universal math. You can't base a coordinate system on how tall a guy's boat is.
You really can't.
Okay.
But it gets worse because we haven't even factored in atmospheric refraction yet.
Refraction, like bending light.
Yes. The Earth's atmosphere is not empty space. It's a thick soup of gases, and it acts like a giant, curved optical lens.
Okay.
So when starlight or sunlight enters our atmosphere, it gets bent. Have you ever noticed how right at sunset, the sun looks kind of squished or flattened at the bottom?
Oh yeah, it looks like an oval instead of a perfect circle sometimes.
That is refraction happening in real time. The light from the bottom edge of the sun is passing through thicker atmosphere than the light from the top edge, so it gets bent more, pushing the image upward.
Wait, really? The atmosphere is literally lifting the image of the sun above where the physical sun actually is.
Yep, it's like a cosmic mirage.
Yeah.
And the amount of bending changes constantly based on air temperature, humidity, barometric pressure, water temperature.
Okay, point taken. Your visible horizon isn't just angled wrong because of your height. It's actually bouncy and distorted by the weather.
Exactly. You cannot build a rigorous universal mathematical grid on a foundation made of optical illusions and variables. So we scrap the visible horizon for the theoretical math.
So we move one step inward to the sensible horizon. The sources describe this one as a plane passing straight through the observer's eye, perfectly parallel to the ground below them.
Right. Imagine holding a carpenter's level right up to your eyes, making sure the bubble is perfectly centered, and then shooting a laser beam straight out in every direction.
Okay, see?
That flat sheet of light cutting through your pupils is your sensible horizon. It just ignores the curve of the Earth completely.
But even the sensible horizon isn't the ultimate baseline. To do the real math, the materials move us to the rational horizon. And this is where I really need you to help me, because when I read this definition, my brain just kind of broke.
I know exactly the concept you're going to bring up. Let's hear the definition.
Okay, so the definition is a great circle on the celestial sphere whose plane passes through the center of the Earth, perpendicular to the observer's zenith nadir line.
Quite a mouthful.
Yeah. So let me visualize this. I'm standing on the deck. I draw a line straight down from my feet, through the crust, through the mantle, all the way down to the molten core of the Earth.
Roughly 4,000 miles down, yeah.
Right. Then, down there in the core, I draw a massive flat plane slicing through the center of the planet, exactly 90 degrees to that vertical line. And the source material is telling me that this plane, buried 4,000 miles beneath my boots, is the baseline for measuring the stars in the sky above my head.
It seems completely absurd on its face, doesn't
It's
it?
totally absurd. I
Oh.
mean, I'm standing on the crust. I'm not down in the core. Why wouldn't I measure from where I am actually standing?
It's a really fantastic question. And resolving that confusion requires accepting one of the most counterintuitive, mind-bending realities of astronomy.
Okay, I'm strapped in. Let's have it.
It forces us to grapple with the concept of true infinity. In navigation, we treat the celestial sphere, this imaginary dome of stars surrounding us, as having an infinite radius.
Right, okay.
The stars are so incredibly, unimaginably far away that the physical size of the Earth itself is mathematically meaningless. It's basically zero.
Wow. It's really hard to hold that kind of scale in your head.
It is. Let's try a thought experiment. Imagine you are standing on the surface of the Earth, and you draw a straight line from your eye, your sensible horizon, all the way out to a star.
Okay, I've got a laser beam from my eye to a star.
Now imagine a second person is standing in the exact center of the Earth. They draw a second laser beam, the rational horizon, out to that exact same star.
So we have two parallel laser beams 4,000 miles apart.
Right. But because the star is practically an infinite distance away, those two lines never converge in any measurable, meaningful way. To the star, that 4,000-mile gap is just an imperceptible rounding error. It's nothing.
So from the perspective of the star, my eye and the center of the planet are literally occupying the exact same point in space.
Precisely. If you project both planes out to the edge of the infinite celestial sphere, the plane of your sensible horizon and the plane of the rational horizon effectively merge.
They just become the exact same line painted against the backdrop of the stars. The distance just vanishes.
Yeah, exactly. And by dropping our mathematical baseline down to the exact center of the Earth, we achieve something brilliant.
We remove all the messy human variables.
Yes, we remove the height of your ship's mast. We remove the atmospheric mirages. We strip away the crust of the Earth itself.
We're left with a perfect, pristine, uncorrupted geometric plane that slices the entire universe exactly in half, completely relative to your specific orientation.
You've got the ground floor. The rational horizon isn't something you look at with your eyes. It's the theoretical ground floor of our mathematical VR headset. All the true, pure measurements of altitude in celestial navigation are referenced down to that perfect plane cutting through the Earth's core.
Yeah, that actually makes so much sense now. But, I mean, a room isn't just a floor. We need vertical elements to build a complete 3D map. We need the walls and, like, a central pillar.
Right. And this takes us to the concepts defining the vertical axis, where we start slicing up the sky. The terminology here is incredibly specific, and for good reason. Every word locks a piece of geometry into place.
The first one the sources mention is the zenith. And they define the zenith as the point on the celestial sphere directly overhead the observer, just straight up.
Yeah.
And the crucial thing I realized is it's totally unique to you. If I walk 10 feet to the left, my zenith moves 10 feet to the left on the celestial sphere.
It is the absolute, unquestionable up in your personal VR environment.
And then we have its twin, the nadir. This is the point diametrically opposite the zenith. It's directly below you, projected all the way out into space on the other side of the planet.
Right, the opposite pole of your personal axis.
Obviously, you can't see the nadir because there's an entire planet in the way, but mathematically, it's the anchor point on the bottom.
And connecting them is the zenith-nadir line. The text says this is the straight line connecting the zenith, the observer, the Earth's center, and the nadir.
I really tried to visualize this as an unimaginably long, incredibly heavy lead plumb bob.
Oh, a plumb bob is perfect.
Yeah. Imagine standing on that deck, and you hold a string with a massive weight. The string extends up from the very top dead center of the sky dome, straight down through the top of your skull, through your feet, through the wooden deck.
Straight through that molten core of the Earth we were just talking about.
Exactly, and out the exact opposite side of the planet to the bottom of the universe.
That is exactly what it is. And the most important geometric feature of that plumb bob line, the zenith-nadir line, is that it is perfectly perpendicular to our ground floor. It hits our rational horizon at exactly a 90-degree angle.
Okay, so we have a flat floor spanning the universe, and we have a central vertical pillar intersecting it. Now, how do we build the walls of our grid?
We build the walls using what are called vertical circles. The geometric definition is any great circle on the celestial sphere that passes through both the zenith and the nadir.
Let's visualize that. You're standing next to your central plumb bob, you look straight up to the zenith, and you draw a sweeping line in the sky straight down to the horizon, and it keeps going through the Earth down to the nadir. You could draw one of these massive hoops through any star in the sky, couldn't you?
You could draw an infinite number of them. One for every star, one for every speck of dust in the universe.
Yeah.
Because they all originate at the zenith and end at the nadir, every single one of these vertical circles hits our rational horizon at exactly 90 degrees. They're perfectly plumb vertical walls.
But out of that infinite number of walls, the source materials highlight one specific vertical circle as being profoundly important for navigation, the prime vertical.
Yes. If you're building a coordinate grid, you can't just have infinite, undifferentiated walls. You need a primary orientation. You need an X and a Y axis.
And a prime vertical provides that.
It does. It's defined as the specific vertical circle that passes through the exact east point and the exact west point of your rational horizon.
So it's a giant celestial hoop that originates at the east point on the horizon, arcs straight up through the zenith right over your head, and plunges straight down to the west point on the horizon.
Exactly. And the reason this specific hoop is so incredibly significant is that it slices your personal sky perfectly into a northern half and a southern half.
Just like cutting an orange in half.
Yeah. And as the source notes, when a star or a planet crosses this specific boundary line, the prime vertical, you immediately know a tremendous amount of data about it without doing a single complex calculation.
Oh, because if a star is sitting anywhere on that specific hoop, it must be bearing exactly east or exactly west from your position.
That's it. If you spot a star on the eastern half of that hoop, you know its azimuth, its compass bearing, is exactly 090 degrees. If it's anywhere on the western half of the hoop, its bearing is exactly 270 degrees.
So the prime vertical isn't just a line, it's like a diagnostic tool.
It is the moment a celestial body's azimuth transitions between the northern semicircle and the southern semicircle. It's a really critical boundary marker in your VR headset.
Okay, Let's take a breath and look at the architecture we've built around ourselves. We're on the ship. We've replaced the bouncy, deceptive ocean with perfect, theoretical, rational horizons stretching out to infinity, originating from the Earth's core.
Right.
We have dropped a vertical plumb bob line straight down through our head. We've drawn infinite vertical walls sweeping down from the zenith. And we have the prime vertical cutting the entire sky neatly into north, south, east, and west quadrants.
The structural frame is totally complete. But right now, it is an empty room. To make it useful, we need to understand how the real physical Earth fits inside this framework.
And this brings us to what I consider the absolute grand aha moment of the entire deep dive. Like the moment where the abstract geometry of the sky connects directly and physically to your flesh and blood body standing on the Earth.
Yes, the concept is simple, but really profound. Altitude equals latitude.
It's so elegant.
This specific relationship is the geometric heart of all celestial navigation. Honestly, if a listener takes only one thing away from this discussion, it should be this. Once you grasp this, the entire sky snaps into focus.
So let's set the stage based on the physics. We know the Earth is a sphere, and it spins on an axis. That invisible axis points out into deep space in two directions, creating two fixed spots on the celestial sphere, the north celestial pole and the south celestial pole.
Right.
In our personal horizontal VR grid, where do those poles show up?
Well, the materials explain that it depends entirely on which hemisphere you are standing in. One pole will be elevated above your rational horizon. It will be visible in your sky. That is called the elevated pole.
Okay.
The other pole will be hidden below your horizon, totally blocked by the mass of the Earth. That is the depressed pole.
So if I'm standing in Times Square in New York, the north celestial pole is somewhere up in the sky. It's the elevated pole. The south celestial pole is depressed beneath my feet.
That's right. The only edge case is if you're standing exactly on the equator.
Yeah. The text points out that in that special case, neither pole is elevated and neither is depressed. Because you are exactly in the middle, both celestial poles rest exactly on your horizon.
They're perfectly balanced on the very edge of your VR vision, 180 degrees apart.
But for almost everyone else on the planet, one of those poles is up in the sky. And the source materials provide a geometric proof to show exactly how high up in the sky that pole is.
And the conclusion of the proof is stated with absolute mathematical certainty. The altitude of the elevated pole above the rational horizon exactly equals the observer's latitude.
Let's walk through the geometry of why that is true, because it's deeply elegant. We don't need to do any heavy algebra. We just need to follow the angles. Walk me through it slowly. I want to be able to visualize every angle.
Okay, let's start with the Earth itself. Imagine the Earth's equator, the belt around the middle. The angle between that equatorial plane and the specific spot where you are standing on the surface is, by definition, your latitude.
Got it. If I'm in New York, I'm roughly 40 degrees north of the equator. The angle from the belt up to me is 40 degrees.
Perfect. Keep that 40 degrees in mind. Now, let's look out at the celestial sphere. The celestial pole is just a laser beam extension of Earth's axis of rotation, right?
Right.
And the celestial equator is just a giant expansion of Earth's physical equator. Think about an axis of rotation. By the laws of geometry, an axis of rotation is always exactly perpendicular to its equator.
That makes perfect sense. A pole sticking through a spinning plate is at a 90-degree angle to the plate.
So the angle between the celestial pole and the celestial equator is rigidly locked at 90 degrees.
Okay, I'm with you.
Now, bring your attention back to our observer-centric grid, our VR headset. We already established our central pillar, right? The zenith, the point straight overhead, and the rational horizon are our floor.
Right. The plumb bob meets the floor at a right angle. The zenith is 90 degrees up from the horizon.
So follow the interlocking logic. The angle from the celestial equator to the celestial pole is 90. The angle from your rational horizon to your zenith is 90. Because these two systems, the absolute celestial equator and your relative personal horizon, are tilted against each other by your specific latitude, the geometry forces a mirror effect.
A mirror effect? How so?
Well, the angle between your rational horizon and the celestial equator exactly equals your latitude.
Let me make sure I follow. The angle at which the absolute equator cuts across my personal sky is equal to my latitude.
Exactly. And since the celestial pole is locked 90 degrees away from that equator, and your zenith is locked 90 degrees away from your horizon, It mathematically guarantees that the altitude of the pole above your horizon is the exact same number as your latitude.
I came up with an analogy for this when I was reading the notes because I'm a visual learner and the angles were getting a little jumbled in my head.
Ah.
I want you to think of this geometry like a giant, rigid, cosmic seesaw.
Ooh, a seesaw. Okay, paint the picture for me.
Okay, imagine you are standing on the Earth's equator. At the equator, your latitude is 0. According to our golden rule, the altitude of the celestial pole should also be 0.
Right. And it is. We just said that at the equator, the pole rests flat on the horizon.
Yes, the seesaw is perfectly balanced. So imagine the celestial equator is a giant arc going straight overhead, intersecting your zenith, and the North Pole is resting right on the northern edge of your horizon.
I see it.
Now, I start walking north. I am physically moving up the curve of the Earth, which means I'm increasing my latitude.
You're tilting your VR headset.
Exactly. As I walk north, my zenith, my definition of straight up, has to move north with me to stay over my head. This physical tilting forces the giant arc of the celestial equator to slide down towards the southern horizon behind me. I am pushing one side of the cosmic seesaw down.
You are lowering the equator behind you.
Right, and because the celestial pole is locked at a rigid 90-degree angle to that equator, as I push the equator down behind me, the North Pole is forced to tip upward in front of me.
It rises above the northern horizon.
It rises. And because it's a rigid 90-degree system, it rises by the exact same amount that I walk north. If I walk north 10 degrees of latitude, I push the equator down 10 degrees, and the pole pops up exactly 10 degrees above my horizon.
That is a phenomenal way to visualize it. The observer is physically and inextricably linked to the geometry of the sky through that cosmic seesaw. Your latitude is not just a number on a map. It's a physical force that dictates the angle of the heavens.
Change your latitude, and the pole moves up or down in your sky by the exact same amount.
Exactly. So what does this actually mean practically for our terrified navigator on the dark ocean? It means that finding out how far north or south you are, finding your latitude, is almost criminally easy if you know what you're looking at.
It really is the most direct piece of navigational data you can gather. The materials use a specific example. An observer, standing at a latitude of 44 degrees north, will look into the night sky and find the north celestial pole at an altitude of exactly 34 degrees above their horizon.
And this is where observers in the northern hemisphere have a massive stroke of astronomical luck. We happen to have a bright, easily identifiable star sitting almost exactly on top of that mathematical pole, Polaris, the North Star.
Yeah, the materials note that Polaris isn't perfectly on the pole, but it's just 0.7 degrees away. It's practically a bullseye.
Which means if you're lost at sea anywhere in the northern hemisphere and you pick up your sextant, shoot Polaris, and measure its altitude above the horizon, that number is essentially your latitude.
Just like that.
Yep, the Polaris is 35 degrees above the horizon. You're roughly at 35 degrees north latitude. It's a near instant direct reading.
You don't need the heavy almanac. You don't need complex spherical trigonometry. You just look at the sky, and the sky literally shows you your location on the Earth. Altitude equals latitude.
It really is an incredible realization.
It proves that you're not just a passive observer of a generic night sky. The sky you see is a mathematical mirror reflecting your exact geographic location. Your physical body tilts the heavens.
It's a profound, almost philosophical connection between the micro scale of a human being standing on a deck and the macro scale of the turning of the celestial sphere.
Speaking of the turning of the celestial sphere, that brings us to the next massive concept we have to tackle today. We've built our tilted VR headset grid. We know where the floor is, we have the walls, and we know exactly how our latitude tilts the central axis.
Right.
Now we have to turn the engine on. We have to make the sky move.
The engine driving every single movement we're about to discuss is, of course, the physical rotation of the Earth beneath our feet.
Yeah, the sources recap a foundational astronomical fact here. The Earth rotates from west to east on its axis, completing one full rotation in approximately 24 hours. And because of that west to east spin, all celestial bodies appear to move east to west across our sky.
It's entirely an illusion, of course. The stars are fixed. We are the ones hurtling backwards. But from our perspective, trapped inside the VR headset, the entire dome of the universe is spinning east to west.
And it spins at a very specific, reliable rate. If the Earth turns a full 360 degrees in 24 hours, the math shakes out to a steady rate of 15 degrees per hour. Every hour that passes, every star in the sky moves 15 degrees to the west.
To track that movement across our observer-centric sky, we need to introduce one more crucial reference line. We've talked about the prime vertical slicing the sky east and west. Now we need the line that cuts the sky north and south. The materials call this the observer's celestial meridian.
The observer's celestial meridian. Okay, how do we draw this one?
The geometric definition is a great circle that passes through your zenith, your nadir, and both of the celestial poles.
Let me trace that out. It's a giant circle. It starts at the exact north point on my rational horizon, goes up through the elevated pole, continues up through the zenith straight over my head,
Yep, keep going.
goes down to the exact south point on my horizon, and then wraps underneath the Earth, passing through the nadir and the depressed pole before coming back up to north.
That is the complete 360-degree circle. It is essentially your specific line of longitude projected infinitely outward onto the dome of the sky. But practically speaking, navigators divide that massive hoop into two distinct halves, the upper celestial meridian and the lower celestial meridian.
Let's start with the upper. The text says this is the half of the meridian that contains the zenith and the elevated pole. So it's the half of the hoop that you can actually see, the part that arcs above the rational horizon.
Yes. And it is not an overstatement to say that this is arguably the most important line in the sky for a navigator. When a celestial body rotates through the sky and crosses this specific upper meridian line, it is called upper transit.
Upper transit.
Astronomers sometimes call it meridian passage or culmination.
It's basically the VIP moment for a star.
Absolutely. Think about the arc a star makes. It rises somewhere in the east, climbing higher and higher into the sky. When it hits that upper meridian line, the exact north-south dividing line, it has reached the absolute peak of its arc.
Oh, wow.
Yeah, it's at the highest altitude it will reach for that entire day. The moment it crosses the meridian, it begins its descent towards the western horizon.
The materials also tie this to the concept of hour angle, which we touched on earlier as measuring angular distance westward. When a body is sitting exactly on the upper meridian, its local hour angle, or LHA, is exactly 0 degrees.
The stopwatch has hit 0. The new daily cycle begins.
So why is this moment so special? Why do navigators obsess over upper transit? Like, why is it better to take a sextant sight when the star is at its peak rather than when it's just rising or setting or halfway up the sky?
It all comes back to avoiding terrifying math. Remember earlier when we talked about sight reduction, the process of reconciling your personal horizontal observation with the universal equinoctial almanac to find your location?
Right, getting the two maps to talk to each other?
Normally, to do that math, you have to solve a complex spherical triangle called the navigational triangle. It involves calculating 3 points: the celestial pole, your zenith, and the unknown celestial body, the star.
Sounds complicated.
It is. The math requires calculating azimuths, zenith distances, and running through complex trigonometric functions like spherical cosines.
Yeah, that sounds like a total nightmare to do by hand on a rocking ship.
It's incredibly prone to human error. But at the exact moment of meridian passage, at upper transit, the star is sitting exactly on the north-south line. This means its azimuth is exactly true north, 1,000 degrees, or exactly true south, 180 degrees.
Okay, so
So you don't need to calculate its compass bearing because you already know it is perfectly aligned with the pole and your zenith.
oh, the 3 points of the triangle, the pole, the zenith, and the star are all lined up on the exact same meridian circle.
Yes, because they are all on the same line, the complex, scary spherical triangle just collapses into a simple, straight one-dimensional line. All the trigonometry completely vanishes.
The source notes that at this moment, quote, latitude can be found by a simple arithmetic combination of the observed altitude and the body's declination.
No trig required, just simple addition or subtraction. You wait for the star to hit its absolute highest point, you take the altitude reading with your sextant, you look up the star's declination in the almanac, you add or subtract the two numbers, and boom, you have your precise latitude.
That is wild.
It is the easiest, cleanest, and most accurate celestial sight you can possibly take. It is the holy grail of a day's navigation.
You literally just wait for it to hit the peak, do some first-grade math, and you know exactly where you are. That is brilliant. Okay, so that is upper transit. What about the lower celestial meridian?
The lower celestial meridian is the opposite half of the hoop. It passes through the nadir, straight under your feet, and through the depressed pole. By definition, it is entirely below the rational horizon.
So when a star continues its rotation and crosses that lower half, it's called lower transit. Its local hour angle is 180 degrees. It has traveled exactly half a day since its upper transit. And for the vast majority of stars, this event happens completely underneath the Earth, totally invisible to us.
That's true for most stars. But the materials make a very crucial distinction here regarding a specific class of stars called Circumpolar stars.
Circumpolar, meaning going around the pole.
If a star is located very close to the elevated pole, its entire circular daily path might be completely above your horizon. It never actually sets. For those specific stars, lower transit occurs above the rational horizon.
Oh, so you can physically watch the star swoop down, hit its absolute lowest point in the northern sky without dipping below the sea, and then immediately start climbing again.
Exactly. Which
Uh-huh.
is a perfect segue into exactly how these stars move. We know they spin around the pole from east to west, but what is the actual physical shape of that path across our sky dome? The materials introduce the concept of diurnal circles.
Diurnal simply means daily, the daily circle.
The physical reality is stated as, because the Earth rotates on its axis once per day, every celestial body appears to trace a complete circle around the elevated pole once in approximately 24 hours.
And here is the formal definition we need to dissect. The diurnal circle of a body is a small circle on the celestial sphere, parallel to the celestial equator.
This concept is where we finally bring the absolute map and the relative map together in motion. The celestial equator is a fixed ring. The stars all have a fixed declination, meaning they live at a fixed permanent distance north or south of that equator.
Okay, I follow.
So as the sky spins, a star has to stay in its lane. It traces a path that is perfectly rigidly parallel to the equator.
Let me visualize this. My observer's latitude tilts the whole sky. It tilts the central axis and the celestial equator like our cosmic seesaw. But a specific star's declination determines which circular track it rides on while that tilted sky spins.
Precisely. Let's walk through the different possible tracks a star can take, because it completely changes how we experience the sky.
Let's start with the cleanest geometry. Scenario 1, zero declination. A star sitting exactly on the celestial equator.
Because it lives on the equator, its diurnal circle is the celestial equator itself. It traces the largest possible hoop across the sky.
And the geometry of this path is perfectly symmetrical. If a body has zero declination, it will rise at exactly the true east point azimuth 0 and 90 degrees. It will arc overhead, and it will set exactly at the true west point azimuth 270 degrees.
And because that massive circle is bisected perfectly by the rational horizon, the star spends exactly 12 hours above the horizon and exactly 12 hours below it.
It perfectly splits the day in half. And what's wild is that it doesn't matter if you are standing in New York or Argentina or Japan. If the star is on the equator, it behaves exactly like that.
It is universal. But of course, most stars are not on the equator. What happens if the star is shifted away from it?
Let's assume we are observers in the northern hemisphere for this. Scenario 2. A star with northerly declination. It is located somewhere north of the celestial equator.
Because its fixed address is north of the equator, its circular track is shifted northward. It is a smaller hoop spinning parallel to the big equatorial hoop. Now think about our tilted VR headset.
Okay, it's tilted.
When that smaller northward track intersects our rational horizon, it doesn't intersect at east and west anymore. The geometry forces the intersection points further north.
So as the materials explain, a star with northerly declination will rise north of true east, it will climb up, reach upper transit, and then it will set north of true west.
And there's a massive consequence to this geometry. Because the track is shifted north, more than half of the swinkle is exposed above the horizon. This means the star spends more than 12 hours in the sky.
Wow.
Yeah, the higher the northerly declination, the smaller the circle, the more of it is exposed, and the longer the time above the horizon.
This clicks instantly if you just think about the sun during the summer. In the northern hemisphere summer, the Earth's tilt gives the sun a northerly declination. What happens?
Long days.
Exactly. The sun rises in the northeast, it arcs high across the sky, it sets in the northwest, and the days are incredibly long. It spends much, much more than 12 hours above the horizon.
Which leads right into the extreme circumpolar case we mentioned. If the northerly declination is high enough, the circular track shrinks and gets so close to the pole that the entire hoop sits completely above the rational horizon. The star never sets. It just spins in a circle around the pole forever.
Conversely, what happens if the star is on the other side? Scenario 3, southerly declination.
The exact opposite geometric effect occurs. The track is shifted south of the celestial equator.
So the star rises south of true east, it transits very low in the southern sky, and it sets south of true west. And because most of its circular track is hidden below the tilt of our horizon, it spends less than 12 hours above the horizon.
Think of the winter sun. Short, cold days. The sun barely peaks over the horizon in the southeast, traces a low, miserable arc, and sets early in the southwest.
And if the southerly declination is extreme enough, the entire circular track is pulled below the rational horizon. The star never rises. It remains perpetually hidden by the Earth. Observers in New York will simply never see the stars that cluster tightly around the south celestial pole.
So declination dictates the specific lane the star runs in, and your latitude dictates the tilt of the track. Together, those two factors determine exactly where a star will appear to pop up over the edge of the world. And navigators have a very specific, dedicated measurement for tracking exactly where that rising happens.
The materials introduce the concept of amplitude, which is a word that gets thrown around in physics a lot, usually meaning the height of a wave. But here, it is a highly specific, localized coordinate.
It is a measurement that is only valid and only used at the exact split-second moment a body is rising or setting on the rational horizon.
The formal definition provided is, amplitude is measured from the true east point at rising, or the true west point at setting, toward north or south along the rational horizon.
Think of it as a variation or an offset from true east or true west. If a star rises at exactly true east, its amplitude is 0. It is no offset. But if it rises a little bit north of east, we have to quantify that angle along the curve of the horizon.
The materials give a practical example to show how it's written in the log. They use E 15 degrees N. This means the celestial body rose exactly 15 degrees north of the true east point.
Which, if we translate that into a standard 360-degree compass azimuth, would be 0.75 degrees. True east is 0.90. You subtract 15 degrees towards north, and you get a bearing of 0.75.
Or, if a star was setting, the log might read W 10 degrees S. It's set 10 degrees south of west. West is 270. Add 10 degrees south, and you get an azimuth of 280.
It is an incredibly efficient way to log a localized horizon event. But what is truly fascinating here, and where we are going to have to slow down and really chew on the math, is the formula the materials provide to calculate this. Because there's a mathematical relationship between the rising point, the star's track, and your tilt.
Yes, the source drops a formula on us. The sine of the amplitude equals the sine of the declination divided by the cosine of the latitude. Let me just repeat that. Sine of amplitude equals sine of declination divided by cosine of latitude.
I know audio math can be really tough to follow, but we have to unpack the underlying logic of this fraction. We don't need to memorize sine and cosine tables, but we need to understand what dividing by a fraction does to the geometry of the sky, because it reveals something spectacular.
I'm with you. Let's start at the simplest place on Earth, the equator. If I'm standing on the equator, my latitude is 0 degrees.
Okay. If you recall basic trigonometry, the cosine of 0 is exactly 1.
Right. So if we plug that into the formula, the denominator is 1. The sine of the amplitude equals the sine of the declination divided by 1.
And anything divided by 1 is just itself.
Yeah.
So the formula collapses. At the equator, the sine of the amplitude exactly equals the sine of the declination. They're a 1-to-1 match.
Meaning, if a star has a permanent declination of 20 degrees north and I'm on the equator, it will rise exactly 20 degrees north of east. Its amplitude is 20. The offset matches the track perfectly.
Yes, the geometry is perfectly flat and undistorted. But now, I want you to start walking north. You are moving away from the equator. Your latitude is increasing.
Let's say I walk to a latitude of 60 degrees north.
Mathematically, as an angle increases from 0 to 90, its cosine shrinks. The cosine of a number greater than 0 is a fraction of decimal less than 1. For instance, the cosine of 60 degrees is exactly 0.5.
Okay, my denominator is now 0.5. What happens mathematically when we divide something by a fraction?
If you take a number and divide it by a fraction smaller than 1, the resulting answer gets larger. If you divide 10 by 0.5, the answer is 20.
Ah. So, let's bring it back to the formula. As I move towards the poles, my cosine of latitude gets smaller and smaller, so I'm taking my fixed declination and dividing it by a smaller and smaller fraction, which forces the resulting amplitude to get larger and larger.
Precisely. And visually, what that means is that the rising point of the star is stretched further and further along the horizon. Let's use our star with a declination of 20 degrees north again.
Okay. At the equator, it rose 20 degrees north of east.
But if you travel to a latitude of 60 degrees north, you plug the numbers in.
Yeah.
You are dividing the sine of 20 by the cosine of 60, which is 0.5. If you do the trigonometry, you find that the star now rises roughly 43 degrees north of east.
That is massive. The star didn't change its lane. The absolute map of the universe didn't change at all. The star is still exactly 20 degrees north of the celestial equator.
Right, the star is fixed.
But because my personal observer-centric VR headset is tilted by 60 degrees, the geometry forces the interception point between the star's track and my horizon to slide dramatically northward.
The rising point stretches. And if you go even further north, to say 80 degrees latitude, the fraction gets so small that the amplitude stretches all the way to 90 degrees.
Oh, wow.
Yeah, the star doesn't even rise in the east anymore. It just skirts along the northern horizon. This formula perfectly captures how the static, absolute universe is distorted by our relative perspective on a curved, spinning rock.
That is genuinely incredible. It's just a simple fraction, but it holds the secret to how the visual shape of the sky stretches and warps based on where you stand.
We have successfully built the entire system. We know our rational floor, our vertical walls, our elevated pole, our latitude tilt, and the spinning, stretching tracks of the diurnal circles.
Which brings us to the final piece of the puzzle, nailing down the specific coordinates. We've watched the stars sweep across our grid, but if a navigator wants to freeze time and log a star's exact 3D position in the sky at a specific random second, what are the final numbers they write down in the logbook?
The materials define three primary coordinates to lock in a position in the horizontal system: true altitude, true zenith distance, and azimuth.
Let's do a final review of these to make sure we have them locked in. First up, true altitude. We've been using the word altitude, but the formal definition is specific. The angular distance of a celestial body above the rational horizon measured upward along the vertical circle passing through the body.
The most important word in that entire definition is true.
Because what you see isn't the truth. The text is very careful to note that the word true distinguishes this mathematical measurement from the observed altitude, which is the raw number you read off the metal arc of the sextant.
When you look through the sextant, you are gathering raw, dirty data. You're using the bouncy visible horizon. Before you can use that number, you have to apply mathematical corrections to clean it.
Like what kind of correction?
You have to account for index error in the instrument, the dip of the horizon caused by your height, the atmospheric refraction bending the light, and even the semi-diameter of the sun or moon if you were shooting them instead of a star.
You literally have to scrub the human elements out of the data.
Once you clean the data with all those corrections, you finally arrive at the true altitude, the exact, geometrically perfect angle above that theoretical rational horizon passing through the Earth's core. It ranges from 0 degrees perfectly flat on the horizon to 90 degrees perfectly straight up at the zenith.
Then we have the second coordinate, true zenith distance. The definition is the angular distance from the zenith down to the celestial body, measured along the same vertical circle.
So altitude measures from the floor up, and zenith distance measures from the ceiling down.
And what I absolutely love about this is the beautiful, undeniable simplicity of the math between these two measurements. True altitude and true zenith distance are perfectly complementary. The formula is just zenith distance equals 90 degrees minus altitude.
It is a totally closed system. The distance from the rational horizon to the zenith is rigidly, permanently 90 degrees. So if a star is resting exactly on the horizon, its altitude is 0, which means its zenith distance is 90. It is 90 degrees away from straight up.
And if a star climbs up the wall to an altitude of 30 degrees above the horizon, it must be exactly 60 degrees away from the zenith. 30 plus 60 is 90. If it climbs to an altitude of 80 degrees, it's 10 degrees zenith distance. They will always, without fail, add up to 90.
It is a perfect seesaw of its own. As altitude increases, zenith distance decreases in exact proportion.
And finally, the third coordinate to lock in the 3D position, azimuth. The definition is a horizontal direction to a celestial body, measured clockwise from true north around the rational horizon, from 1,000 degrees to 360 degrees.
It is simply the compass bearing of this specific vertical circle wall that the star happens to be sitting on at that exact moment.
So if I'm the navigator, and I give you a true altitude of 45 degrees and an azimuth of 120 degrees, I've given you a precise, unambiguous 3D location in my personal sky. You turn 120 degrees from north, you look exactly halfway up the wall towards the zenith, and boom, there's the star.
You have taken the infinite chaotic swirl of the universe and pinned it down to a single point on a grid constructed entirely around your own body. You have mapped the chaos.
And that is exactly what we set out to do at the beginning of this deep dive. Let's retrace the journey we just took. We started out standing on the dark, swaying deck of a ship, overwhelmed by stars. We needed a reliable ground floor, so we threw away the visible ocean and projected a pristine, rational horizon straight through the Earth's molten core out to infinity.
We established our center pillar, dropping the plumb bob line connecting our zenith to the nadir.
We drew infinite vertical circles down from the zenith to build our walls, paying special attention to the prime vertical slicing the sky east to west.
We located the celestial poles, discovering the profound geometric truth of the cosmic seesaw. that the altitude of the elevated pole instantly and perfectly reveals our physical latitude.
We turn on the engine of Earth's rotation, defining the observer's celestial meridian and watching stars hit their absolute peak altitude at upper transit, giving us the easiest mathematical calculation in all of navigation.
We trace the diurnal circles of the stars, realizing that their fixed declination and our tilted latitude dictate exactly where they rise, how their rising amplitude stretches along the horizon, and how long they stay in the sky.
And finally, we lock the entire 3D space down with the hard numbers: true altitude, zenith distance, and azimuth.
It truly is one of the most remarkable intellectual achievements in human history, born entirely out of the desperate practical need to not get lost and die at sea.
So, why does all of this dense geometry matter to you, the listener, sitting at home or driving in your car today? Because understanding the horizontal system proves that you are not just a passive observer of a generic night sky. The sky you see above you tonight is not a generic wallpaper pasted above the Earth.
It's totally unique to you.
It is a mathematical mirror reflecting your exact geographic location. Your physical presence, your specific latitude standing on the curve of this planet, physically tilts the heavens. The sky belongs to you, shaped entirely by where you stand.
That is a very powerful realization to walk away with. And I want to leave you with one final mind-bending hypothetical to explore on your own. A thought experiment that pushes everything we've discussed to its absolute geometric breaking point.
Oh, I love a good thought experiment. Lay it on us.
We know, as an absolute, unshakable geometric fact, that the altitude of the elevated pole equals your latitude. We prove the cosmic seesaw. Now, imagine you get on a nuclear icebreaker and you travel north, all the way north. You travel to exactly 90 degrees north latitude, the geographic North Pole. You are standing exactly on the top of the spinning top.
Okay, I am at 90 degrees north.
What happens to your VR headset grid? If your latitude is 90 degrees, the altitude of the North Celestial Pole must be 90 degrees, which means the pole is exactly at your zenith. It is directly, perfectly straight overhead.
The axis of the universe is going straight through my spine.
Remember the 90-degree rule. If the pole is at your zenith, the celestial equator must be exactly 90 degrees away from the pole, which means the celestial equator becomes your rational horizon. They merge into the exact same line.
Wait, the absolute equator of the universe is lying flat on the ground all around me in a 360-degree circle.
Yes. Now turn on the engine of daily motion. The Earth spins. The stars trace their diurnal circles parallel to the equator. But the equator is the horizon. So the stars do not rise in the east and set in the west. The stars trace endless, perfect, horizontal circles all the way around you. A star with an altitude of 20 degrees will slide horizontally across the sky at exactly 20 degrees altitude, 360 degrees around your head, forever.
No rising, no setting, just a dizzying, endless carousel.
The entire concept of upper transit loses its meaning because the stars never change altitude. The concept of amplitude ceases to exist because nothing ever crosses the horizon. So the provocative question is this: if the stars never rise and never set, and the sun, which is just a star tracing a diurnal circle, slides horizontally around you for 6 straight months without ever dipping below the horizon, how would physically experiencing that warped geometric reality alter your fundamental human perception of what a day even is?
That is a lot to chew on. The geometry literally breaks time. Next time you find yourself standing outside at night, maybe not on the deck of a ship in the middle of the ocean, but just standing in your backyard or on a balcony, look up at that dizzying swirl of stars. Remember the invisible architecture of your rational horizon buried in the core of the Earth, your zenith straight above, and that cosmic seesaw tilting the pole just for you. You are the absolute center of that specific universe.